This video is an assignment for my course, Design and Analysis of Algorithms. And so I looked at the detailed summary of the course, scanning through the topics, thinking which one would be the best topic to make a whole video about. And I laid my eyes on the most popular topics of the course, divide and conquer algorithm and dynamic programming. But making a video explaining any one of these techniques, going into the technicalities, seemed pretty boring. So instead, I'm going to try and see how and when these methods are used, and despite the time they save, are they always worth it? The three methods that I'm going to focus on are dynamic programming, divide and conquer, and mathematics. Computer science students are probably looking and thinking, but math isn't a problem solving technique. It is. Despite the popular belief, computer science engineers aren't coders who sit for hours in front of a black screen with green fonts making websites or hacking the internet. The engineers, problem solvers, who essentially use mathematics and computers to solve different problems. Your computers at the end of the day just doing basic math, adding ones and zeros, with some to the bigger pictures of AI, robotics and ML. Let's first see what dynamic programming and divide and conquer algorithms actually are. Let's start with the utmost basic, a function. A function is a piece of code that takes in some input, runs some code, and gives out some output based on the input. And while writing a program, you many times call the function. That's where you write out its name and tell it to use these inputs, some input to give out some sort of output. Now, a recursive function is a function that calls itself. So if you were to look at the code, you would see the same function name in there somewhere, with the inputs slightly changed. Now, divide and conquer algorithms are algorithms that use recursion to take the original program and then divide them into many smaller manageable problems. You would normally call those problems subproblems. Now, in many situations, this is a great technique. Look at this code, for example. This function takes an integer, n, then prints numbers in ascending order up to the number n, starting from 0. Here you can see how the function calls itself, but reduces the input by 1 until it has reached 0, and then starts printing the numbers. But this technique also falls flat in a number of scenarios. Take the Fibonacci sequence for example. A Fibonacci sequence is where the next number in the sequence is the sum of the two numbers before it. So you would start with a 0 and a 1, and then onwards add the two numbers just before it. If we use a recursion, we see a process that is not optimal at all. Take a look at this step. To find the sequence at position 7, you need to find the sequence at position 6 and 5. But to find the sequence at position 6, you once again need to find the sequence at position 5. And so you end up calculating the same thing twice. This problem only multiplies as you go down the ladder, with the Fibonacci sequence of 2 in this case being calculated 8 times. This redundant step is extremely wasteful and just unacceptable to an engineer. And so dynamic programming comes into play. Dynamic programming basically takes this concept of dividing problems into subproblems and removes the need to calculate the same thing multiple times. Now, if you really want to learn dynamic programming, there are a few properties and different methodologies used. But since this isn't the focus of my topic, I won't bother explaining all that. Let's, however, look at one way this is implemented. Let's take the example of the Fibonacci sequence. Now we make an array whose index number corresponds to the Fibonacci position, and the value of its result is stored at that index. An array is basically a list where we can store numbers, and all those numbers have a corresponding index number in that array so that we can access it. We take in our input. We already know that fib of 0 should be 0 and fib of 1 should be 1. Now we work our way up. We say that fib of 2 is the sum of the numbers before it, that is fib of 0 and fib of 1. We take those values from the array, add them up, and then store them back in the array at index 2. We keep doing this till we reach our desired value n, at which point we again look at our array and add the number at position n-1 and n-2. Let's look at one more question. This question is called the Josephus problem, and if you want a better explanation of it, I'll leave a video by number file down in the description. The problem goes like this. N people are sitting in a circle, and they're numbered sequentially in a clockwise manner. starting from number 1, each person kills the person to their left. In case that there are 2 people left, the person opposite will be killed. Given a number n, you have to find out at which position you should sit to survive. Now a few of you have already started seeing the pattern. Let's say that there are 5 people. The killing process is going in a loop. That is, that there are multiple iterations of it. And after each iteration, a certain number of people are dead. See where I'm going with this? After each iteration, the number of people reduces, and so it becomes a sub-problem. Here in case of 5 people, after the first iteration, number 2 and number 4 are killed. And this now becomes a problem with 3 people instead of 5. Also here, for the first iteration, instead of the person at position 1 holding the sword, the person at position 5 is holding the sword. Clearly you can use a recursive function. And since there is no repetition of cases, you don't even have to use dynamic programming. But isn't there a faster way to do this? If you see each iteration again, you would see that in each iteration, only even numbered people die. That means in the case when n is a power of 2, the person at position 1 always wins. In case that n is not a power of 2, we can still write n as a power of 2 plus some constant, let's say L. And after L people die, it again becomes a power of 2, and the person holding the sword then will survive. And so given a power of n, we can directly find the position using this. This is where knowing a little math can save you a whole lot of trouble. The time complexity with the first solution was log base 2n. The second solution was the time complexity was 1. Math is the root of algorithms and data structures, and many times students don't realize this. In fact, the first computer scientists were mathematicians who wanted to automate the process to speed things up. Having ideal code though isn't always the end goal. In my last codeathon, I got so obsessed with this one idea I had, which would solve this equation in the time complexity 1. But I didn't end up solving the question in time. So be wise with what you have to do and what is worth it. And don't try to finish your assignment in the last couple of hours.